Okay, so good evening. My name is Devlina Maiti. I'm a research scholar and I'm an NPTEL TA for the course Basic Real Analysis, and the course instructor is Professor I.K. Rana. So in this session, we will discuss about limit of a function and continuous function. Okay, so let's start this session. So what is limit of a set? So if A is a subset of R and C belongs to A, then C will be called a limit point of A if there exists a, if for every neighborhood of this C, if for every neighborhood of C, so there exists a point which is different from this C such that intersection of this A is non-empty. This means every neighborhood of C contains a point of A which is different from this C, right? Then C is a limit point of this A. Now we'll discuss about limit of a function. Right. So what is the definition? So definition is, let A subset of R and let C be a limit point or cluster point, same thing. Cluster point of A. Now for a function f from A to R, a real number L is said to be a limit of this function f at this point C if given any epsilon greater than 0, there exists a delta greater than 0 such that whenever x belongs to this, so x belongs to A, and whenever x belongs to this delta neighborhood of C, then fx belongs to the epsilon neighborhood of L. Means mod fx minus L is less than epsilon, right? So C is a limit of this function. I think there is a sound from okay. So this C is a limit of f, L is a limit of this function f at the point C if given any epsilon greater than 0 pre-assigned, we will find an delta greater than 0 for which whenever this x belongs to the delta neighborhood of C, then fx will be on the epsilon neighborhood of L, right? So this is same as what? Whenever x belongs to the delta neighborhood of C, this will imply fx belongs to the epsilon neighborhood of L, right? Okay, so this is the definition of limit. Now let's find out limit for some functions. Okay, so examples. So first one is the simplest one. So let x belongs to c x. So this is what? This is nothing but c. Now let's prove this by epsilon delta definition. So this limit is c. So this means first epsilon greater than 0 is given. Now we have to find a delta greater than 0, right? So choose delta to be epsilon. Now whenever x belongs to the delta neighborhood of c, that is x minus delta to x plus delta, right? This implies fx, which is nothing but what? Here the function is x, so fx is x, so x belongs to same thing, the delta neighborhood or epsilon neighborhood, since delta is epsilon neighborhood of c. Here c is what? C is fc. So whenever x belongs to the delta neighborhood of c, we found that fx belongs to the epsilon neighborhood of fc, which is c here. So this means c is the limit of this function fx, which is x, right? So this is a simple example. Now let's take different example. So let's find out x tends to 0, x sine 1 by x. So this limit will be what? This limit will be 0. That we have to check. So here the function is what? Function is x sine 1 by x, right? So what is psi x minus this 0 is what? Is which is nothing but mod of x, mod of sine x. Now sines varies in -1 to 1. So modulus of sine x is less equals to 1. So this is less equals to mod x, right? Now for given epsilon greater than 0, given. So we have to find delta greater than 0, for which this, so this is here is L, this is 0 is L, right? So whenever mod of x minus, the point is here c is 0, this is less than delta, this will imply psi x minus L, which is also here is 0, is less than epsilon. This we have to find out, right? This delta we have to find out, for which this happens. Whenever x minus 0 is less than delta, it will imply this is less than epsilon, right? Now since mod of psi x is less equals to mod x, we will choose what? We will choose delta to be epsilon. Now delta is epsilon means what? Whenever mod of x is less than epsilon, what we have? We have mod of, from this equation, we have mod of psi x less equals to mod x, right? Now our mod x is less than epsilon, so this is less than epsilon. So we have found out that whenever mod x less than delta, mod of psi x minus 0 is less than epsilon. So 0, this means mod of psi x minus 0, which is L, less than epsilon. So limit x goes to 0, psi x is what? Psi x is 0, right? So 0 is the limit of this sine x sine 1 by x. right? Okay. Now there is a criteria to find out the limit, the sequential criteria. So what is the sequential criteria for limit? Okay. So let f is a function from a to r where a is a subset of r, right? And c be a cluster point or limit point of this a. Then the following are equivalent. Okay. So the first one is what? Limit x goes to c fx is L. Here C belongs to A. Okay. And for every sequence xn in A that converges to C such that not all the xn's are C. For all n belongs to n, then f of xn goes to converges to L. This means what? The limit of f at the point C exists and it is equals to L. It will imply what? There is a sequence for every sequence. There could be many sequences. So for every sequences xn which converges to C, then it will imply f of xn will converge to L. And this is vice versa. This is equivalent. So if the limit exists, then this will happen for every sequence of this xn. This condition holds. And for if this condition holds, then we can say that the limit of f at the point C exists and it is equal to L. Okay. So this is the sequential criteria for limit. Now, when we say that the limit does not exist, so this is the criteria for limit. If it is exists, then we have to find it in this way. Now, what is the negation, or when we say that the limit does not exist or the limit does not go to L? So the negation is what?
Then for which I have to say negation.
What? I do not. Uh,
For which statement I have to negate one?
Negation. Okay, I am writing the term. The statement I am writing. Okay. Negation means when it does not have a limit. F is a function and suppose C belongs to this A.
No,
Right.
I'm asking for which statement I have to negate. I have to say the negation for the entire statement, ma'am.
When we will say it is a negation.
Okay, ma'am.
I am writing the statement. You will see. Negation means what? So let a subset of R and F is a function and C belongs to R be a cluster point of A. Right. Now, if L belongs to R, then if does not have a limit at C, if and only if there exists a sequence xn in A xn converges to C, but f of xn will not converge to L, then we say that this f does not have a limit at C, right? So f does not have a limit at the point C means if we take any point L, then we have to find a sequence xn which converges to C, but f of xn does not converge to L. Here the condition was for every sequence xn which converges to C, f of xn converges to L, right? So the negation will be we have to find there exists at least one sequence xn which converges to C, but f of xn will not converge to that L, right? Then we say that L is not a limit of this function f at the point C, right? Now there is another one, if so it may happen that this xn converges to C, but this fxn does not converge to any point. Here it was if L is a point and f of xn converges to L, but this does not converges to this point L. It is convergent, but it may converge to some other point L1, right? Then L is not a limit. Now here the condition is f does not have a limit. So this means fxn may not converge. So if xn converges to C, but this fxn is divergent. Okay. So there are two possibilities. Okay, now we'll see some examples.
Ma'am,
Yes.
what is the difference between A and B? Are they same or
No,
different?
A and B are different. A means in A, we are saying that L is not a limit of C. The point, there is a point L belongs to R, which is not a limit point, which is not a limit of F at this C. Then we are saying that xn converges to C, but fxn, see here this fxn may converge to some L1. It is convergent, fxn is convergent, but it converges to some other point. Then we are saying L is not L. We have taken the point L. So L is not a limit point, not a limit of this function f. But fxn converges. Here in B, we are saying that f does not have a limit. This means xn, there is sequence xn converges to C, but fxn does not converge. Means it is divergent. Here this fxn may converge to some other point, but here fxn does not converge. It may be some converges to infinity. Then we cannot find a point. So this is the difference. Okay.
Okay, ma'am.
Okay, let's see some example where this is not a limit. We will get some examples. Okay. First one is, so limit x goes to 0, 1 by x. So does this limit exist? See, this will fall into the second condition, this B. Here the limit does not exist. But we have to prove that. So to prove it, we have to find, so in B, what do you have to prove? We have to find a sequence. There exists a sequence xn. So you have to find a sequence xn which converges to the point. Here the point is what? Here the point C is 0. So we have to find a sequence xn which converges to C, but f of xn, that is f of xn is what? 1 by xn does not converge. So what we will choose? Here C is 0, so this is 0. So xn converges to 0. So the simplest sequence is what? 1 by n, right? So 1 by n converges to 0, converges to the point. This is fine, this part is fine, xn converges to C. Now what is f of xn? F of xn is what? This is n, right? 1 by 1 by n, so this is n. So this does not converge, this goes to infinity. So this f of xn does not converge, right? So we have found a sequence which converges to the point 0, this 0, but f of xn, that is 1 by xn, does not converge. So this means this function does not have a limit at x equals to 0, right? So limit x goes to 0, 1 by x does not exist, right? Okay, so let's see next example. So this is called the sine function, which is 1 when x greater than 0, 0 when x equals to 0, and minus 1 when x is less than 0, right? This is the definition of this function. So okay, so this looks like what? This is 0, so it's minus 1. So whenever x is less than 0, this is constant minus 1, and at the point 0 it is 0, and after 0 it is constant 1.
Is that SGM? What does it refer to, ma'am? In the second example.
SGN, this is a sine function. This is defined
Okay.
in this way. So whenever x greater than 0, so this one is not taken, is open, and at 0 it is 0, right? So this function looks like this. Now what is the limit of this function at x equals to 0? This is the question. Does this limit exist? So the question is, limit x tends to 0 exist or not? So does this exist?
Yes, ma'am, it will exist.
Why? And what is the value? If it is exist, so there must be some value.
Yes, ma'am, when n tends to 0, the sign n will be also 0.
See, whenever when x tends to 0, there are two possibilities. We can approach 0 from the left side and the right side, right? When we are approaching it from the left side, it is constant minus 1, so it will give you minus 1. The limit will be minus 1. And when you will approach from, this will give you minus 1. And when you approach it from the right side, from the positive side, it is constant. The fx is constant plus 1. So the limit will be constant 1. And both are not equal, right? Also we can say that the limit does not exist by this sequential criteria. So we will find a sequence xn which converges to 0, but f of xn will not converge to 0. Okay, I will give an example. So choose xn to be minus 1 to the power n by n. Right. Now this sine function is nothing but, if we write in the simplest form, so it is nothing but mod x by x when x not equals to 0 and 0 when x equals to 0. This is the same thing. See, when x greater than 0, then mod x is x. So mod x by x will be 1, and when x is less than 0, mod x will be minus x. So mod x by x will be minus 1. Right? This is the same function. Now what is sine of?
Ma'am, how did you get the idea of forming that xn, ma'am? What
See,
is the reason to form the sequence as minus 1 per n by n?
there is no idea, like you have to, if you solve many problems, then you will get some idea. But right now you are starting, so it may be difficult for you, but when you start to solve the problems, more problems, then you will get an idea how to find an example, construct some sequence. You will get an idea. Okay, but you have to try, you have to solve many problems. Okay, so now what is sine of xn?
Can I form xn as minus 1 per n, ma'am?
Because we will see that this xn will go to 0, but this sine xn will not converge. That's why I have chosen in this form, because in sine xn there will be some minus term. Okay, I'm writing and then you will.
Okay, ma'am.
So what is sine xn? This is mod of xn by xn, right? When x is not 0. So what is mod xn? Mod xn is 1 by n, and xn is what? Minus 1 to the power n by n. So it is nothing but minus 1 to the power n, which is same as minus 1 to the power n. Right? So sine xn is what? Minus 1 to the power n. So this is not a convergent sequence. Right? It will oscillate between minus 1 and 1. Right? So we have found, but xn converges to 0, because if you take any term, because n tends to infinity, this goes to 0. Modulus mod of xn goes to 0, so xn converges. So xn converges to 0, but sine of xn does not converge. Right? So by this definition, by this b, so xn converges to c, but f of xn does not converge in R. So this implies this sine function, a limit x tends to 0, sine x does not exist. Okay, there are some special functions actually. This sine x, this x sine x, sine 1 by x, this you have to remember. These are the basic things. Okay, now we know the definitions of limit. Okay, let's see another example, then we'll go to the continuous function. Okay, so another famous example is what? Sine 1 by x. So how does it look like? So first sine x we have done here a function x sine 1 by x, right? Yes, this function x sine 1 by x. And
Ma'am,
yes,
ma'am, in second example, why we define sin x as mod x by x, ma'am?
this is not sine x, this is signum. This is I am telling it is sine, it is signum function. This is written by sgn. This is not sine function, this is different. This is a name, this is just a notation, sgn. This is
Okay,
not
ma'am.
same as sin x function. This is different. That is the trigonometric function. This is different function. Okay. This signum function, or I am writing this SGN. Okay. This is different.
Yes, ma'am. I mean, answer we define the mod x by x, ma'am. Why, ma'am? Why we define that, ma'am?
Oh, I have not defined. This is the same thing. This is this signum function. What I have defined first, that is 1 when x greater than 0, 0 when it is 0, and when x less than 0, this is minus 1, right? This and these two are same. I have just written in terms of x. Mod x by
Okay, ma'am.
mod x by x is same thing, because you see, whenever x is greater than 0, this mod x by x is what? Mod x then will be x, and this is x, this is 1. And when x is less than 0, then mod x by x will be what? Mod x will be minus x when x is less than 0. So this is minus x by x, which is minus 1, right? So this I have written. That's why I have written mod x by x. Okay, this is the same thing, because I have put in mod x by xn form, right? That's why I have written in this form. This is the same function. Okay, now how does it look like, this sine 1 by x? And what about this x sine 1 by x? So we have already seen that limit x tends to 0, x sine 1 by x equals to 0, right? We have already seen that, right? So this, how does this look like? So this is x sine 1 by x, right? So this, when x goes to 0, this goes to 0. So in 0 it is here, and when x is 0, this is oscillate, because this is a sine function, so it will go like this, and in the same thing. Okay, so this is the drawing of what? X sine 1 by x. See, these lines is what? These lines, this is actually y equals to x, and this is y equals to minus x, right? Because we have seen that if this is fx, then mod fx is what? It was less than mod x. So always mod fx is less than mod x. So this x sine 1 by x will always lie between this y equals to x and y equals to minus x, because here mod fx is what? Mod fx is mod x, and in this line mod fx is mod x. Now what about this sine 1 by x? Now how does it look like? See, when x is 0, it is undefined, right? Because there is no value of 1 by 0. So it maps, and this is a sine function, so it will always lie between minus 1 to 1. So this is x, y. So this is 1, this is minus 1. And in 0, it is undefined. So it images, it is dense near 0, and then it will act like the normal sine function. But in 0, near 0, it is dense, and there is no value of at x equals to 0, right? Okay, now we'll see that when x goes to 0, this exists or not. So question is, limit x tends to 0, sine 1 by x exists or not? Okay, you see that this does not exist. So this means what? We have to find sequences where sequence belongs to the point 0 but f of xn does not converge. Okay, so here we'll use two sequences. So from the limit definition it was what? That for every sequence xn which converges to 0, f of xn will converge to the same point, right? Now for this example we'll see that there will be two sequences which converges to c, but the two sequences converges to different point. If the limit exists, then it should be unique, right? But here we'll see that the two sequences will go to different limit. Since it is a sine function, the formation of these sequences is easier. Okay, so first we'll take this sequence 1 by 2n pi. Okay, or n pi, same thing. N pi where n belongs to n, right? So clearly xn goes to 0, right? And take another sequence yn by 1 by right. Since here this n is here, so this will also go to 0 as n goes to infinity, right? So xn and yn both goes to 0. Now what about f of xn? So f xn is what? Sine of n pi, right, which is 0. And f of yn is what? F of yn is sine of which is sine pi by 2, which is 1, right? So we have seen that xn goes to 0, yn goes to 0, f of xn goes to 0 and f of yn goes to 1. So this also claims that the sequence, this limit does not exist, because for every sequence which converges to 0, f of xn, f of this sequence must go to a same thing, must go to the same point. But here this two sequence goes to different point. So this means limit does not exist, because if limit exists then it has to be unique, right? So this implies sine 1 by x does not exist, right? Okay, so you get the idea of limit of a function, right? Now we'll go to the continuous function. So what is a continuous function? So same thing. So let A subset of R and f from A to R is a function and C belongs to A, right? Then we say that f is continuous at C if given any epsilon greater than 0, there exists delta greater than 0 such that whenever x if x is any point in the delta neighborhood of x, then mod of fx minus f of c is less than epsilon, right? See, this is the same definition of this limit. Our limit was what the definition is. See, the same thing. This given any epsilon greater than 0, there exists a delta greater than 0. So whenever x belongs to the delta neighborhood, fx belongs to the L neighborhood of epsilon, right? But in case of continuous function, this L has to be f of c, the functional value of f at the point c, then it is a continuous function. Okay, this is the only difference. So this L is where L is this fc, right? So this definition is same thing as whenever x belongs to the delta neighborhood of c, this will imply fx will belong to the epsilon neighborhood of f of c, right? So this is the same thing as f of a intersection, that is the image of f of this neighborhood n delta c is contained in the delta neighborhood of this fc, right? This is the same thing. Whenever x belongs to this delta neighborhood, fx belongs to n epsilon fc, right? So from here, this is the same thing. Okay, so this means what actually? So continuous function means, so there is some c, point c in a, right? And this is the function, suppose f, this is y x and this is fx, this is the curve function. So c, this is c here, so fc is here, this is our fc, right? Now the definition says given epsilon greater than 0 is given, right? This is already given. So this is fc. So epsilon neighborhood of fc look like what? This portion, right? This is the epsilon neighborhood of fc, right? This portion means this portion. Okay, this is all already belongs to this. So we have to find a delta such that here we have to find delta here such that the image of this delta neighborhood of c, which is nothing but, so image of this what will be from here, if we choose delta here minus delta, so this is our image of this neighborhood n delta c. So f of n delta c is this portion, right? So this portion is what? This portion is contained in the epsilon neighborhood of fc, right? Because epsilon neighborhood of fc is what? Epsilon neighborhood of fc is this blue line. This is all of this in the epsilon neighborhood, because this is minus this is epsilon neighborhood of fc, all this whole curve, and this portion is contained in the epsilon neighborhood of this fc, so that's why it is continuous at the point c, right? Now if it is continuous in the whole a, then we say that f is continuous on this set a, right? So this is the definition of continuous function. Now from the definition of limit, it is clear that, now remark, we say that c belongs to a, so if f is continuous, then from the definition of limit, what? X goes to c fx will be nothing but fc, right? Because in the limit definition of limit, here this fc was what? Fc was L in number, but in case of the continuous function, this fc, this L is the point fc, right?
Ma'am, if you don't mind, can you please repeat the explanation for the graph?
For the
A
graph.
little bit slower.
Okay, I will take this. Okay, 1 second. Suppose the graph is so this is suppose a some a may not be a open interval, but I am choosing this is a, and this is here our c, right? So this is x coordinate, y coordinate, and suppose this is fx, right? This is the graph of fx. Now we have to find out if it is continuous at the point c or not. So first we have to choose a depth epsilon greater than 0, right? And what is fc? Fc is at the point c, the functional value. This point is fc, right? Now take a epsilon neighborhood of this fc, right? So epsilon neighborhood of fc means what? So this is fc. So there will be some, this is what? This is fc plus delta, fc minus delta, right? So minus epsilon, sorry. So this is the epsilon neighborhood of this fc, this portion. This portion means in the functional value it is the whole portion. This. Because all of this point, if we take fx minus fc, then it will be less than epsilon, right? All the values in this graph, in this section, I am outlining by this blue line. So all the points here, if we take any point here, fx, if it is fx, then fx minus c will be what? Modulus value. This will be less than epsilon, right? Because this whole strip, in the whole portion, all of the values is difference. This is fx, right? So this is fc, the mod of fc. So so the difference of this value from fc will be less than epsilon. All of this value here, all the points here in the blue section, it is epsilon distant away from the point fc, right? And now we have to find delta. So suppose delta is here, right? So this is c minus delta and c plus delta. Now what is the image of this section, image of this part? So image of this part is what? This is here and this portion is here. So image of this c minus delta to c plus delta will be this portion, right? So this, if we take here in the image section, so it is contained in this section, fc minus delta to fc plus epsilon, right? So this portion is contained in this section, so that's why it is continuous at the point c. Now you have to check for all the points and then we will say that it is continuous on the whole a. Now do you get it, or I have to? Sorry, this was our curve. Okay. So from the definition of limit and the definition of continuous function, we say that if f is continuous, then the limit of fx at the point c will be this fc, not some random number. It will be it will be the value of f at the point c. Okay, when if it is continuous. Now, okay, now let's see the sequential criteria. Same thing. Criteria for continuity. So function so it is continuous at the point c if and only for every sequence, the same thing for every sequence xn, if xn converges to c, it will imply f of xn converges to fc. In the limit thing, we have written that if xn converges to, for every sequence xn converges to c, f of xn converges to that point, the limit point L, right? Here the limit point is fc. So that's why for every sequence xn converges to c, f of xn must converge to fc. This is a sequential criteria. Now what is the negation or it is discontinuous at a point? Then what do we have to show? So negation or discontinuity criteria. Is what? Same, A is subset of A if the function. Now f is discontinuous at C if and only if, so for every sequence, now in negation it will be there exists a sequence. So there exists a sequence xn in A such that xn goes to C implies f of xn goes to fc in the sequential criteria. So it will be what? Xn will go to C, but f of xn does not converge to fc. It may be convergent, but it has to converge to fc. Converge to fc, right? If you see the examples, then it will be clear. Okay, so first, what is the most easiest example is what? The constant function, suppose say 1, right? So it is continuous. Now by the epsilon delta criteria, so epsilon greater than 0 is given, right? Now you have to find delta. So this function is what? This is 0, this is 1. The whole function is fx equals to 1, right? So if we take any point C and that epsilon neighborhood of this fx, right? So choose any delta. It will be inside this fx minus fc. Fc is less than epsilon, right? So this is constant function. So fx minus fc, c belongs to R, is always 0, right? Because this is 1 and this is 1, so it is always 0. and it is less than epsilon always. So you can choose delta to be any number. Any number is possible. Any positive number will work, right? So whenever C belongs to the delta neighborhood, x belongs to the delta neighborhood of this C, fx will belong to the one neighborhood 1 minus epsilon to 1 plus epsilon, right? Anything, delta can be anything, because for any delta this will happen. Fx minus fc is always 0, so it is always less than epsilon, so it does not depend on this delta. So delta can be chosen any positive value. Now let's go to the next problem. Okay, now what about this signum function I have written, which was what, mod x by x when x not equals to 0 and 0 when x equals to 0, right? So is this continuous at the point 0? It is not continuous because the limit does not exist. So what we have seen is that we have found a sequence xn which goes to 0, but f of xn, this f of xn does not converge to sine of xn goes to 0, so it has to goes to signum of 0, which is defined as 0, so it must converge to 0. But we have found a sequence xn which was minus 1 to the power n by n, so this does not converge to 0. It is not convergent, this sequence, so that's why it is not sin signum x is not continuous at x equals to 0, right? So same thing for sin 1 by x, right? Because limit x tends to 0, sin 1 by x does not exist. If it is exist, then it must match the value of sin of 1 by 0, which also does not exist. So that's why it is also not continuous at x equals to 0. First it has to be exist. First the limit must exist, and it has to match with f of c, the point fc. So what about this x sin 1 by x? X not equals to 0, it is defined at x not equals to 0, because when x equals to 0, sin 1 by 0 is not defined, so that's why fx is x sin 1 by x. Now we have seen that limit x goes to 0, x sin 1 by x is what, 0, right? So if we define this function fx to be x sin 1 by x when x not equals to 0 and 0 when x equals to 0, then this fx, we'll write this capital F, then this capital F is continuous, at x equals to 0. Why? Because limit x goes to 0, capital Fx has to match with what, f0, right? Now it is nothing but x sin 1 by x when x not 0, it is x sin 1 by x, and when x is 0, f0 is what, f0 is 0. So this we have proved, this is true, so that's why this is also true. So this means f is continuous at x equals to 0, right? Okay, now let's see another important example. So A is the whole R, and fx is defined fx is defined to be 1 when x belongs to the rational number, and 0 when x belongs to the irrational number. Okay, right. Now we'll prove that f is not continuous at any point of R. It is nowhere continuous. Right. This is called the Dirichlet function, and this is a very famous example. Okay. So it is not continuous at any point. Right. So for every point we have to find a sequence. So suppose now we'll do it in two cases. Right. So first case is what? So we are choosing a point from the rational number. Okay. So rational and irrational from the whole R. So first let C belongs to the rational number. Now it is not continuous at C means we have to find a sequence xn in R such that to show there exists a sequence xn in R such that xn goes to the point C, but f of xn does not go to fc. Right? Then we will say that it is not continuous at the point C. Right? So what is the sequence we will choose? See, the density theorem says what? What is the density theorem? Density theorem of real number was what? If you are given two real number xy belongs to R, then there exists a rational number. There exists a rational number R belongs to Q such that x less than or less than y. So given any two real number, there is a rational number in between them. Right? So this is the density theorem. Now from this density theorem, we can say that we can find a sequence of irrational numbers which converges to the rational number C. Right? What is this sequence? This is, suppose C. Now C is less than what? C plus root 2 by n. Right? So I am telling that there exists a sequence xn of irrational numbers such that xn will converge to the rational number C. Right? So for this example, xn is C plus root 2 by n. So this will converge to what? This will goes to C. And this xn, all the xn's belongs to the irrational numbers because C is rational, but here this root 2 is irrational. Right? So this xn is a sequence of irrational numbers which converge to the rational number C. Right? So we have found a sequence. And now, so what about f of xn? So f of xn is what? Since xn is all the xn is what? All the xn's are irrational numbers, and I have defined when x belongs to irrational numbers it is 0, right? So f of xn is 0, right? And what about fc? Fc is what? C belongs to rational, so fc is 1, right? So this implies what? This implies f of xn does not converge to fc, because this sequence is a 0 sequence, so 0 sequence it will not converge to 1, right? So it does not converge to fc. This is 0 and this is equals to 1. So we have found a sequence which converges to this point c, xn goes to c, but f of xn does not converge to fc. It converges to 0, but it does not converge to fc, right? So this means what? This means c, f is not continuous. So f is not continuous at any rationals. Okay. Now case 2 is what? Case 2 will choose c is irrational. C is irrational number. Now we have to find a sequence xn which converges to C, but f of xn does not converge to fc. Now in the similar way, we will by the density theorem, we'll find a sequence yn of rationals. Density theorem gives the existence of this sequence. Okay, now we have to choose the sequence. So there exists yn of rationals in R such that yn will go to the irrational number c, right? Now what we choose? We'll choose yn to be do you know the box function? This box x means it is the largest largest integer which is less than x. It's the largest integer which is less than x, less than or equal to x, because if x is integer then it will be x less than or equal to x. Means if it is 5.1, box of 5.1 will be what? 5, right? And 5.9 will also be 5. This is the largest integer which is less than. So box x is always less than x, right? X minus 1. Okay, this is a definition, this part, definition of box x. Now we have what we have chosen? We have chosen yn to be box of nc plus 1 by n. Now since there is a 1 by n form, so now where does it converge? We have to prove that this yn goes to c, right? So now box of nc is less than nc, right? And nc is less than box of nc plus 1, right? There is a difference of 1. So this implies and this is nothing but this yn. So we have found that c is less than yn. right? Now yn is what? Yn is nc plus 1 by n, which is right, and nc by n is what? Nc by n is less than c, so it is less than c plus 1 by n. So yn is less than c plus 1 by n. So if we combine these two, what we have? We have c less than yn less than c plus 1 by n, right? So this we get. So now by the sandwich theorem, limit of n goes to infinity, c plus 1 by n is c, which is limit n goes to infinity yn, right? By the sandwich theorem, limit of yn is c. So we have proved that yn converges to c. Now what about f of yn? So now f of yn is what? Now all the yns were what? These were irrational numbers. Sorry, yn is rational number. Our c is irrational, and we have formed a sequence of rational numbers, because box of nc, c is irrational, but box of nc is what? This is an integer plus 1 by n, so this is a rational number, right? So our yn is now in rational number. So what is f of yn? So if x is rational, then f of x is 1. So our all the yns are rational, so this is 1, right? And f of c is what? 0, because x is irrational, c is irrational, as c is irrational number, right? So f of yn does not converge to fc, because this is a constant sequence 1 and this is 0. So the constant sequence 1 cannot go to 0, right? So this means f is not continuous at any irrational number. So we have proved that f is not continuous at any rational numbers, and now we have proved that f is not continuous at any irrational number. So this means f is continuous nowhere in R, right? So this is the proof of this example. So this function, this fx is this is the Dirichlet function. This is a famous function, and this function is continuous, not continuous at any point. Means this is nowhere continuous in R, right? So we have found an example of a function which is continuous nowhere in R. Now, can you give an example of a function which is continuous at only point, at a single point of R, and discontinuous everywhere? Everywhere means otherwise it is discontinuous, and it is continuous only at a single point. Can you give an example of such a function? So question number 6. Function which is continuous only at a single point, suppose x equals to 0, only at x equals to 0, means it is discontinuous at every other point. Okay, so can you give an example of such a function? Okay, so there is a technique, right? So consider this function x when x belongs to q and 0 when x belongs to irrational, right? So what we have defined, fx is x if it is rational and 0 if it is irrational number, right? Now we'll prove that this function is continuous only at x equals to 0. So if we take any other point, so first we'll show that at x equals to 0 this is continuous, right? So what is fx minus 0? This is, sorry, fx minus f0 you have to take. Minus f0 is mod fx, because f0 0 is rational, so 0 is x means 0, so this is mod x, mod of fx, and which is nothing but mod x, right? Because if it is rational, suppose x belongs to R, right? So x may be rational, may be irrational, right? So if x is rational, then it is mod x, and if it is irrational, okay, so mod x is what? Mod x is mod x if x belongs to q, and 0 if x belongs to irrational, right? This is the function mod x, mod of fx minus f0, right? So now epsilon greater than 0 is given, so we have to choose delta. So choose delta is epsilon, because here mod of fx is mod x, right? So this means whenever mod x is less than delta, this will imply mod of fx minus f0, which is nothing but mod x or 0. If it is 0, there is nothing to prove, right? So if it is mod x, then it is less than epsilon, right? So this will imply what? This will imply f is continuous by the definition, epsilon delta definition of continuity, right? Given any epsilon greater than 0, here given any epsilon greater than 0, we'll get a delta greater than 0 such that whenever mod of x minus c is less than delta, mod of fx minus fc is less than epsilon. So here c is 0, so fx minus fc is fx minus 0, f0. This is less than epsilon. So f is continuous at x equals to 0, right? Now we'll prove that if c is any other point which is not 0, then f is discontinuous at that point. So suppose c is not equals to 0, c belongs to R and c not equals to 0, right? Now we'll prove this in the same way, in the same technique we have used in this example. That is, if c is rational, then we'll find a sequence of irrational number. So suppose c is a rational number, right? Now in the same technique we'll find a sequence. So there we can say that there exists a sequence xn in the irrational number such that xn goes to c, right? So we have formed a sequence of irrational number which goes to the rational number c, right? Now what is f of xn? F of xn is what? Xn is irrational number, and at irrational point it is 0, so f of xn is 0, and fc is what? Fc is c, right? So this means 0 goes to c, and c is non-zero, so this is not possible. So this is not possible. as c not equals to 0, right? So f of xn does not converge to fc. So this means f is discontinuous at any rational number, right? Because c is, we have chosen c is rational. Now similar thing, if x belongs to c belongs to qc, if c is a irrational number, we can find a sequence yn in rational number such that yn will go to c, a sequence of rational number converging to the irrational number c, right? So now what about f of yn? So f of yn is what? Yn, right? And fc is, because yns are rational number and c is irrational, so fc is 0. So this means what? This means yn, if it is continuous, so f of yn goes to fc. f of yn is yn and fc is 0. So it is not convergent because c is non-zero. Yn does not converge to 0. So this implies f of yn does not converge to fc, right? C is non-zero. First thing, we have proved c for c equals to 0, and here where this c is non-zero, right? That's why this is not possible. So this means f is not continuous at any rational numbers other than 0, because we have proved that it is continuous at 0 and it is not continuous at any irrational numbers, because 0 is a rational number. 0 right. So we have proved that this function, this fx equals to this is continuous only at a point x equals to 0, right? Now if we say that, if I tell you to give an example of a function which is continuous only at 2 points, x equals to 0 and x equals to 1, then what will you do? Now how to form this example? It will be similar like this, okay? Now if I tell you to give an example of a function which is function in R, defined in the whole R, which is continuous only at x equals to 0 and x equals to 1. Now I am saying that it is continuous only at 2 points, x equals to 0 and x equals to 1. Then how to form this? This is in the same method. So we will define fx is x into x minus 1 when x belongs to rational and 0 otherwise. Okay. Then when x goes to c fx, it will be what? It will be c into c minus 1. Now there will be two sequences, a sequence of rational, a sequence of irrational number goes to this point c. So this will be 0. So c will be either 0 or 1, right? So for c 0 and 1 it will be continuous, and for the other point it will be discontinuous. You can prove this in the similar method, right? So if I tell you to give an example of a function which is continuous at some finite number of points, you can form this example in this way, right? X into x minus a1, x minus a2, like that. Okay, for finite number of points, right? Now you try to give an example for countably many points. So this is an exercise. Example of a function which is continuous at a countably infinite point. For countably finite point, you can give an example like this from the same method. Now we have to give an example for countably infinite point. Continuous at a okay. This is an exercise. You try this. Okay. Okay. So let's go to the thing. Numbering. Okay, let's do it quickly. Let fx is x square plus so fx is defined in this way when x is not equals to 1, right? Now the question is, can we define the function f at the point x equals to 1 in such a way that f becomes continuous, right? See, we have already done this for the function x sine 1 by x, right? Okay, let's check this out. Yes, so if f is, so we have defined here f is what? F is x sine 1 by x when x is not equals to 0, and we have seen that limit x goes to 0 sine 1 by x is 0. Now we have defined at the point 0, so it is not defined at x equals to 0. So at the point x equals to 0, we have defined the value 0, the value of the limit of this function, such that this becomes f0, so this f becomes continuous, right? So we need to assign the value at x equals to 0, the limit point, the limit value of this function. We have to assign that point, then it will be continuous, right? Then f becomes continuous at x equals to 0. So for this function, first we have to find limit x goes to 1 fx. Now this value we'll assign, so suppose this is L, right? Then we'll assign f of 1 to be this L, right? Because for continuity the limit has to be f of c when x goes to c, right? So first we have to find out the limit of this function when x goes to 1. So see, when x goes to 1, the denominator is 0 and the numerator is also 0, so this is 0 by 0 form. So we have to find limit x goes to 1 fx. So it is what? See, x square plus x plus minus 2 is nothing but x minus 1 into x plus 2, right? So this is nothing but x plus 2. Now we can put this value, so this is 3. So when x goes to 1, limit of this value is 3. So define, so I am defining now fx is which is given when x not equals to 1, and 3 when x equals to 1, right? Now this function, this fx is continuous at x equals to 1. Because why? Because limit x goes to 1, fx is f1, right? As this is true, this is continuous at x equals to 1, right? Okay. Now there is an important theorem which is called the intermediate value theorem for continuous function, right? So what is this theorem? Intermediate value theorem. Right. So what does it say? It says suppose f is continuous, f from I to R is continuous, where I is an interval. Right. Now if there is any 2 points belongs to I and if it's to R such that so there is our suppose there is our interval I and there is some points a b in I, right? So f is the mapping, so there is some fa and fb, right? So if we take any value k in between fa and fb, then we say that then there exists a point, say point C in between AB, in between this AB, such that FC is equals to K, right? So this K is nothing but f of C. So whenever we are taking two different points in the codomain, in the image domain, FA and FB, right? And if K is any point in between, then this is the pre-image of FA, this A, and this is the pre-image of FB, which is B. Then there will be a point C in between this AB such that the image of this C is K, right? So this is the intermediate value theorem for continuous function only. This is true, not for any other functions, for continuous function. Okay, so let's see some problems from this theorem. So show that the polynomial so using this theorem we'll prove this, that this polynomial has at least two real roots. Roots mean what? Say C is a root of a polynomial px if and only if P of C is 0, right? If P of C is 0, then C is a root of this polynomial Px. polynomial px, right? So we'll use the intermediate value theorem. Okay, now what is p0? So our p is this polynomial, so p0 is -9, right? So it is less than 0. Now what is p of 2? P of 2 is clearly it is greater than 0, right? So there is 0, this is 2. At 0, p0 is somewhere, oh sorry, p0 is less than 0. So there is some p0 -9, so it is less than 0, right? In the if we draw the graph, it is in the lower portion, right? Because it is negative, right? And p2 is what? P2 is positive, which is somewhere here, right? This is a positive value. So from this point, if we, since it is a continuous function, polynomials are continuous, right? X to the power 4, x cube, they are all continuous functions. So since it is a continuous function, it will go like this, right? May not be like this, may be like this, but if it will go from this point to this point, right? And it is continuous, so there will be no gap, no hole in this line, right? So this means it will cut this portion 0 to 2, this interval, at least one times. It may cut more than that, but it will cut at least one time, right? So in between 0 to 2 there must be a root of this polynomial, right? So if it cut here, this portion is a root, and if the function is this one, then this will be roots, right? So at least one root is there. Do you get it? So there is at least one root of px in 0 to 2, right? By the intermediate value property. Why? Because intermediate value property said this is positive and this is negative, right? This is positive and this is negative. So in between positive and negative, 0 is a number, so 0 is in between p0 and p2, right? Now since it is continuous, the intermediate value property says if k is a number in between this fa and fb, so here this is p0 and p2, there is 0, right? So between this 0 is there, so this imply between a and b there is a number c such that fc is k. So this imply there exists c in between 0 to 2 such that p of c is 0, right? So p of c is 0 means c is a root of px, right? Since it is continuous, by the intermediate value property, there is a root in between 0 to 2. So it says it has at least two real roots. So we have found that at least one root is there and it is in between 0 to 2. Now we have to find other root. So let's take f of -10, right? Then it will be 10 to the power 4 minus 7 and you will see that this will be positive number, right? So there is our minus 10, and in minus 10, if p of minus 10 is positive, it is some positive value, right? So there must be a, so the curve is continuous, so it must be like this, or at least it must cut at least one time, right? Since it is continuous. By the intermediate value property it is clear, but if you see, it is, since it is continuous, this is positive and this is negative, so the curve in between minus 1 to 0 must cut the real line, this is the real line, x axis, at least one time, right? So same thing, so p0 is less than 0, 0, and oh sorry, it is p, right? So p0 less than 0, p of minus 10, it is positive. So in between minus 10 to 0, by the intermediate value property, there exists C2 belongs to this minus 10 to 0, such that f of C2 is 0, right? It is clear? So in between, oh, this is p, so C2 is a root of px. So here is our some c1 and here is our some c2, so it has at least two real root. Okay, so we have proved that px has, so px has at least two roots, at least two real root, right? Because it may be more than that, but at least two is there, because it may be cut, it may cut the real line 2 to 3 times in between 0 to 2, but at least one is there, right? You get it, right? Okay, now let's take another example. From using this theorem we will prove that. Okay. So if is defined in 0, 1 to R and f is continuous, yes, so this is a question. So f is continuous in 0, 1 and f takes only the rational value, right? This means if x belongs to 0, 1, fx belongs to rational number. Fx is never a irrational number, right? Then is f a constant function or not? Right. Now one thing I have to, so by the intermediate value property, a remark is that let I be an interval and f from I to R be continuous. Then f of I will be an interval. This is from the intermediate value property, because if fa and fb is there, if we take any point in between them, then this is some FC, and C belongs to in between f of C, where C between A and B, right? So if I is an interval, then Fi will be this interval. So if AB interval is there, then FAFB is interval in the image domain, right? This is a remark of this intermediate value property. We can use here like that, or we can prove this from the general definition of intermediate value property. So if it is constant function or not. So suppose it is not constant. So suppose f is not constant. So f is not constant means what? If we take any 2 points, they are distinct, right? So if a b belongs to this 0 1, so this will imply fa not equals to ab. Means there exists AB, some AB belongs to 0 1 such that FA is not equals to FB, right? Because F is not constant. Now FA is not equals to FB and F is continuous function. So by the intermediate value property, so if so there exists some K in between them, right? By the density theorem of real number, if x and y is any 2 points, there must be a rational number or irrational number in between them, right? So there exists K belongs to R such that FA is less than K, less than FB, right? Now by the intermediate value property, K is what? K is the density theorem there exists a irrational number K belongs to R such that FA less than K less than FB. Okay, we can find many rational and irrational number in between FA and FB since they are not equal, right? So now by the intermediate value property, since F is continuous, by the intermediate value theorem, there exists C belongs to this in between A and B such that this FC is K, right? So FC is K means what? And K is what? K belongs to irrational number. So F taking an irrational point. But by our hypothesis, we say that F takes only rational values, right? So this is a contradiction since FC is irrational number. So this is a contradiction. As F takes only rational values. Right? So this is the proof of this example. So it is a very important theorem, this intermediate value property, right? If f is continuous and f is defined on an interval, then fi will also be an interval, right? And if you have watched the video lectures, then you have seen that if f is defined on a compact set, then the image of this compact set f of a will also be compact set. So these are some properties of continuous function. Now what about open set? If G is open and f is continuous, does it imply fg is open? some question. So F is from R to R say continuous. And suppose G subset of R is open. Now is F of G open? Is it true? Take the constant function fx equals to 1, x belongs to R, right? So now take, if G is any open set, open in R, fg is what? Fg is the singleton 1, and this is not open, right? This is closed but not open, so fg is not open. It's not open, right? Now if G is closed, you will see that fg will not be closed. May be closed for some time, for some example, but in general you cannot say if G is open, fg is open, if G is closed, fg is closed, right? There are counter examples for this, right? But there is some thing, theorem, if G is open in the image domain here, so if suppose F is what? F is from R to R, right? Here if G is open, you cannot say fg is open, right? This is our example. But if G is open, some G, or say, right, A is open in the image domain, this image codomain, then the inverse of this, that is F inverse A, will be open, right? This can be proved, and you can see any book. I will solve this, but there is already time, so I am just writing the theorem. So the theorem says, if, and it is an if and only condition. So F inverse A is what? F inverse A means what? F inverse A contains all those y belongs to R such that there exists some x belongs to A such that fx equals to y, right? The image of, inverse image of A. So the theorem says a function from R to R is continuous on R if and only if F inverse G is open in R whenever G is open. And similar for closed set. A function if from R to R is continuous on R if and only if F inverse F is closed in R whenever F is closed. Okay, see any book for these references, okay, and prove this. Okay, so I'll stop here, and in the next class I will discuss about uniform continuity. Okay, if you have any doubt, you can ask now. Okay, I guess you don't have any doubts. Okay, then we'll meet in the next class. All right.
Yes, thanks.
Okay then. Okay, let's end this call.